The reading for Lecture 4. Some simple numerical programs. Now that we have covered some basic Python constructs, it is time to start thinking about how we can combine those constructs to write simple programs. Along the way, we'll sneak in more language constructs and some algorithmic techniques. Exhaustive enumeration. The code in Figure 3-1 prints the integer cube root, if it exists, of an integer. If the input is not a perfect cube, it prints a message to that effect. The operator exclamation point equal sign or bang equal not equal means not equal. Comment find the cube root of a perfect cube. We create a variable x that we set equal to the value of the output of the input function being put into the integer function. So we show the user enter an integer, they type something in, press enter, and then whatever they put in is then passed into the integer function and converted into an integer, right? Because otherwise it would be a string even if it's just a number, remember? So we set the value of x using that. We create a variable ants that we set equal to 0, and then while ants to the third power is less than the value of passing in x to the absolute function, that is the absolute value of x. While that's true, update the value of ants equal to its own current value plus 1. If ants cubed is not equal to the absolute value of x, print the current value of x followed by the string is not a perfect cube. Or else, if x is less than 0, then update the value of ants to negative ants, the negative of its own value. And then print the string cube root of followed by the current value of x followed by the string is followed by the variable ants. This is using exhaustive enumeration to find the cube root. The code first attempts to set the variable ants to the cube root of the absolute value of x. If it succeeds, it then sets ants to negative ants, if x is negative. The heavy lifting, such as it is in this code, is done in the while loop. Whenever a program contains a loop, it is important to understand what causes the program to eventually exit the loop. For what values of x will this while loop terminate? The answer is all integers. This can be argued quite simply. The value of the expression ants to the third power starts at 0 and gets larger each time through the loop. When it reaches or exceeds the absolute value of x, the loop terminates. Since the absolute value of x is always positive, there are only a finite number of iterations before the loop must terminate. This argument is based upon the notion of a decrementing function. This is a function that has the following properties. It maps a set of program variables into an integer. When the loop is entered, its value is non-negative. When its value is less than or equal to 0, the loop terminates, and its value is decreased every time through the loop. It decrements instead of increment. Now, what is the decrementing function for the while loop in Figure 3-1? It is absolute value of x minus ants cubed. Now, let's insert some errors and see what happens. First, try commenting out the statement ants equal 0. The Python interpreter prints the error message. This name is not defined because you didn't set it. You didn't assign a value to this variable ants. Because the interpreter attempts to find the value to which ants is bound before it has been bound to anything. Now, restore the initialization of ants, replace the statement ants updated to the value of ants plus 1 by ants updated to its own current value, and try finding the cube root of 8. After you get tired of waiting, enter Control-C. Hold down the Control key and the C key simultaneously. This will return you to the user prompt in the shell. Now add this statement, print the string value of the decrementing function absolute value of x minus ants cubed is, followed by the variables the absolute value of x and minus ants cubed at the start of the loop, and try running it again. This time it will print Value of the decrementing function abs x minus ans cubed is 8. Over and over and over again. The program would have to run forever because the loop body is no longer reducing the distance between ants to the third power and the absolute value of x. When confronted with a program that seems not to be terminating, experienced programmers often insert print statements such as the one here to test whether the decrementing function is indeed being decremented. The algorithmic technique used in this program is a variant of guess and check called exhaustive enumeration. We enumerate all possibilities until we get to the right answer or exhaust the space of possibilities. At first blush, this may seem like an incredibly stupid way to solve a problem. Surprisingly, however, exhaustive enumeration algorithms are often the most practical way to solve a problem. They are typically easy to implement and easy to understand. And in many cases, they run fast enough for all practical purposes. Remove or comment out the print statement that you inserted for debugging and reinsert the statement and update the value of ans equal to its own current value plus 1. Now try finding the cube root of this number that without the helpful commas is going to be difficult to read, so I'm not going to. The program will finish almost instantaneously. Now try big ol' huge honkin' number. As you can see, even if millions of guesses are required, runtime is not usually a problem. Modern computers are amazingly fast. It takes less than 1 nanosecond, 1/1000th of a second, to execute an instruction. It's hard to appreciate how fast that is. For perspective, it takes slightly more than a nanosecond for light to travel a single foot, or 0.3 of a meter. Another way to think about this is that in the time it takes for the sound of your voice to travel 100 feet, a modern computer can execute millions of instructions. Just for fun, try executing the code. max_value set equal to the result of passing in the user input to the integer function, enter a positive integer, set I equal to 0, and then while variable I is less than our variable max_value, update the value of I equal to its own current value plus 1, and then print I. Now see how large an integer you need to enter before there is even a perceptible pause before the result is printed. Let's look at another example of exhaustive enumeration. Testing whether an integer is a prime number and returning the smallest divisor if it is not. A prime number is an integer greater than 1 that is evenly divisible only by itself and 1. For example, 2, 3, 5, 111, 119, these are primes, and 4, 6, 8, 62, 710, 561, they're not primes. There's tons of them. The simplest way to find out if an integer x greater than 3 is prime is to divide x by each integer between 2 and x minus 1. If the remainder of any of those divisions is 0, x is not prime. Otherwise, x is prime. The code in figure 3-2 implements that approach. It first asks the user to enter an integer, converts the returned string to an integer, and assigns that integer to the variable x. It then sets up the initial conditions for an exhaustive enumeration by initializing guess to 2 and the variable smallest_divisor to none, indicating that until proven otherwise, the code assumes that x is prime. The exhaustive enumeration is done within a for loop. The loop terminates when either all possible integer divisors of x have been tried, or it has discovered an integer that is a divisor of x. After exiting the loop, the code checks the value of smallest divisor and prints the appropriate text. The trick of initializing a variable before entering a loop and then checking whether that value has been changed upon exit, it's a common one. Check it. So this will test if an integer is greater than 2 is prime. If not, it will print the smallest divisor. X will be equal to whatever the user passes in response to this string. converted into an integer, our variable smallest underscore divisor will start out equal to the Boolean value 9. Not the Boolean value, you know what I mean, whatever. And the for loop for guess in range 2 to x. So starting and including 2, up to but not including the value of x. Remember, if x modulo guess, which, remember also here that guess is just what they're calling it, was I usually, right? It's your index variable that you can call anything. If x modulo guess is equal to 0, then update the value of the variable smallest underscore divisor equal to the current value of the index variable guess. Then break. If smallest divisor is not equal to none, print smallest divisor of the variable x is the variable smallest divisor, or else print x is a prime number, using exhaustive enumeration to test primality. Finger exercise. Change the code in figure 3-2 so that it returns the largest rather than the smallest divisor. Hint: if y times z equals x and y is the smallest divisor of x, z is the largest divisor of x. The code in figure 3-2 works, but it is unnecessarily inefficient. For example, there is no need to check even numbers beyond 2, since if an integer is divisible by any even number, it is divisible by 2. The code in figure 3-3 takes advantage of this fact by first testing whether x is an even number. If not, then it uses a loop to test whether x is divisible by any odd number. While the code in figure 3-3 is slightly more complex than the code in figure 3-2, it is considerably faster, since half as many numbers are checked within the loop. The opportunity to trade code complexity for runtime efficiency is a common phenomenon. But faster does not always mean better. Am I right, ladies? There is a lot to be said for simple code that is obviously correct and still fast enough to be useful. Test if an integer greater than 2 is prime. If not, print smallest divisor. Okay, so same as before with x, same as before with the variable smallest divisor, but then we start out by checking if x is even with modulo. If x modulo 2 is equal to 0, then the smallest divisor must be 2. Or else, if it's not, if that's passed, then for guess in range 3 to x in increments of 2, if x modulo guess is equal to 0, then the smallest divisor equals guess. Break. If smallest divisor is not equal to none, print smallest divisor of x is smallest divisor. Else, print x is a prime number. Sorry, something in my eyeball. This is a more efficient primality test. Yeah. This whole exercise is really funny to me. A finger exercise. Write a program that asks the user to enter an integer and prints 2 integers. Sorry, it's really funny conceptually to me to make all these videos where I'm reading textbooks to nobody. If somebody's watching this now, then it makes what makes this funny to me moot, you know. But write a program that asks the user to enter an integer and prints 2 integers, root and power, such that 1 is less than power, which is less than 6, and root to the power is equal to the integer entered by the user. If no such pair of integers exists, it should print a message to that effect. Finger exercise. Write a program that prints the sum of the prime numbers greater than 2 and less than 1000. Hint: you probably want to have a loop that is a primality test nested inside a loop that iterates over the odd integers between 3 and 999. Alright, next up we skip to 3.3. A few words about using floats. Most of the time, numbers of type float provide a reasonably good approximation to real numbers, but most of the time, it's not all of the time. And when they don't, it can lead to surprising consequences. For example, try running the code x equal to the float 0.0, and for I in range 10, update the value of x to its own current value at that point in the iteration plus 1/10. If x is equal to 1.0, print the current value of x followed by the string equals 1.0, or else print x is not 1.0. Perhaps you, like most rational people, find it surprising that it prints 0.9999999999999999999999999999999999999999999999999999999999999999999999999999999 is not 1.0. Why does it get to the else clause in the first place? To understand why this happens, we need to understand how floating point numbers are represented in the computer during a computation. To understand that, we need to understand binary numbers. Now, when you first learn about decimal numbers, i.e. numbers in base 10, you learned that any decimal number can be represented by a sequence of the digits 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. The rightmost digit is the 10. I'm not sure what that symbol means, but it's the tens place. No, is the, what? Oh, 10 to the 0th place. Oh, I've never seen it put like that. But, you know, it's the, okay. The next digit towards the left is the 10 to the first place, etc. For example, the sequence of decimal digits 302 represents 3 times 100 plus 0 times 10 plus 2 times 1. How many different numbers can be represented by a sequence of length n? A sequence of length 1 can represent any one of 10 numbers, 0 through 9. The sequence of length 2 can represent 100 different numbers, 0 through 99. More generally, a sequence of length n can represent 10 to the nth power different numbers. Binary numbers, numbers base 2, work similarly. A binary is represented by a sequence of digits, each of which is either 0 or 1. These digits are often called bits, which is an abbreviation of binary digits, by the way. The rightmost digit is the 2 to the 0th place. The next digit towards the left is the 2 to the first place, etc. For example, the sequence of binary digits 1, 0, 1 represents 1 times 4 plus 0 times 2 plus 1 times 1 equaling 5. See, there's 2 possible values, and then 4 possible values, 8 possible values, right? It's, well, or I got that, sorry, 1 and 2 and 4, you know what I'm saying. It's 101 equals 5 in binary. Helpful. How many different numbers can be represented by a sequence of length n? 2 to the nth power. Finger exercise. What is the decimal equivalent of the binary number 10011? Perhaps because most people have 10 fingers, we like to use decimals to represent numbers. On the other hand, all modern computer systems represent numbers in binary. This is not because computers are born with 2 fingers. Mine are. It is because it is easy to build hardware switches, i.e. devices that can be in only one of 2 states, on or off. That computers use a binary representation and people a decimal representation can lead to occasional cognitive dissonance. In modern programming languages, non-integer numbers are implemented using a representation called floating point. For the moment, let's pretend that the internal representation is in decimal. We would represent a number as a pair of integers, the significant digits of the number, and an exponent. For example, the number 1.949 would be represented as the pair 1949 and -3, which stands for the product 1949 times 10 to the -3rd power. The number of significant digits determines the precision with which numbers can be represented. If, for example, there were only 2 significant digits, the number 1.949 could not be represented exactly. It would have to be converted to some approximation of 1.949, in this case 1.9. That approximation is called the rounded value. Modern computers use binary, not decimal, representations. They represent the significant digits and exponents in binary rather than decimal, and raise 2 rather than 10 to the exponent. For example, the number represented by the decimal digits 0.625, or 5 over 8, would be represented as the pair 101 and negative 11. Because 101 is the binary representation of the number 5, and number 11 is the binary representation of negative 3. The pair 101, negative 11 stands for 5 times 2 to the negative third power equals 5 over 8 equals 0.625. What about the decimal fraction 1/10, which we write in Python as 0.1, 1/10? The best we can do with 4 significant binary digits, oh my god, is 0011, negative 101. This is equivalent to 3 over 32, i.e. 0.09375. If we had 5 significant binary digits, we would represent 0.1 as 11001, negative 1000, which is equivalent to 25 over 256, that is 0.0976565. How many significant digits would we need to get an exact floating point representation of 0.1? An infinite number of digits. There do not exist integers sig and exp, significant digits and exponent, such that sig times 2 to the negative x power equals 0.1. So no matter how many bits Python or any other language uses to represent floating point numbers, it can represent only an approximation to 0.1. In most Python implementations, there are 53 bits of precision available for floating point numbers, so the significant digits stored for the decimal number 1/10 will be 11001100110011001100110011001100110011. This is equivalent to the decimal number 01. I'm not even going to try fucking reading that. But pretty close to 1/10. You see 01, but then way down here we got fuzziness. Pretty close to 1/10, but not exactly 1/10. Returning to the original mystery, why does the code mentioned above print 0.99999999999 is not 1.0? We now see that the test x is x equal to 1.0 produces a result false, because the value to which x is bound is not exactly 1.0. This explains why that else clause was executed. But why did it decide that x was less than 1.0 when the floating point representation of 0.1 is slightly greater than 0.1? Because during some iteration of the loop, Python ran out of significant digits and did some rounding, which happened to be downwards. What gets printed if we add to the end of the else clause the code print x is equal to 10.0 times 0.1, it prints false. It's not what our elementary school teachers taught us, but adding 0.1 10 times does not produce the same value as multiplying 0.1 by 10. By the way, if you want to explicitly round a floating point number, use the round function. The expression round, with x and num digits passed in as argument, returns the floating point number equivalent to rounding the value of x to num digits, following the decimal point. For example, print round with 2 to the 0.5 power and 3 passed in as arguments will print 1.414 as an approximation to the square root of 2. Does the difference between real and floating point numbers really matter? Most of the time, mercifully, it does not. There are a few situations where the difference between 0 point shitload of 9s, 1.0, and 1.0 shitload of zeros 1 matters. However, one thing that is almost always worth worrying about is tests for equality. As we have seen, using equal to compare two floating point values can produce a surprising result. It is almost always more appropriate to ask whether two floating point values are close enough to each other, not whether they are identical. So, for example, it is better to write absolute value of x minus y is less than 0.0001 rather than asking if x is exactly equal to y. That is, so is the difference between these negligible rather than are they identical? Another thing to worry about is the accumulation of rounding errors. Most of the time, things work out okay, because sometimes the number stored in the computer is a little bigger than intended, and sometimes it's a little smaller than intended. However, in some programs, the errors will all be in the same direction and accumulate over time. End of reading.